times 1. It didn't say to do 1 times 1759. So Ivan distinguished between this situation and this situation. Perhaps for whatever reason, Ivan did this. But notice Ivan has a little bit more work to do, does he not? Okay. He have, throws away remainders. He's got his 1, 2, 4, 8, 16, 32, 64, 128. In other words, he's doubling the number 1 over and over again. And then his keepers over here, well, notice there's a 54. He throws that away. And he throws away the 1 by the 6. Everything else he keeps, right? All right. Now, Svetlana knows the commutative principle of multiplication. She's happy with this rule and says, if I'm going to multiply 1 times something, something times 1, I might as well multiply 1 times that something if it's going to be easier, right? Which it is, certainly, in Russian peasant multiplication. If you look back at her work, that's done in a hurry, whereas Ivan took a little bit longer. Okay? So the answer is still the same. You've got to give him credit for persistence. Ivan, as you will discover, is a persistent individual. Okay. So, before we say, well, Ivan is a peasant, so what do you expect? We won't want to say that about him. Take another look at what happens if Ivan keeps track of whether his numbers in the doubles column are keepers or not in the remainders column. My wife also objected to my grammar here, but I'm going to try and explain it. He does this to remind himself of what he's throwing away when he's throwing away a row of numbers and to double check his work. So here's what he does. He now has a column over here of remainders. He says when 1759 is divided by 2, there's a remainder of 1. See? When 879 is divided by 2, there's a remainder of 1. Down here, when 54 is divided by 2, what's the remainder? 0. Huh? So, when 6 is divided by 2, we got a remainder of 0. Everywhere else, he has a remainder of 1. Now, look what Ivan is doing. He's adding this number times 1 plus this number times 1 plus this number times 1 plus this number times 1. Look at that. Well, actually, he's adding 1,024 times 1 plus 512 times 1 plus 256 times 0 plus 128 times 1 plus 64 times 1 plus 32 times 0 plus 16 times 1 plus 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 times 1. Does that remind anybody of anything? Notice that all the numbers in the doubles column are powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3rd, etc. Well, in fact, Ivan has converted the number 17,059 base 10 to the number 110,110,11111 base 2. The Russian peasant multiplication is a method of reading from the bottom up in the remainders column. You see, you have to read from down here up. See, 1, that's your first digit, 110,110,11111, and you can do this on a good calculator too. If you got one, you can convert the number to a different base. All right, everybody with me on that? Okay, so Ivan has found a way, probably by mistake, knowing Ivan, to convert numbers from the decimal base to the binary base. Now, the question that people have been dying to know, how does RPM work, Russian peasant multiplication? Notice if the halvers column was even numbers all the way down to the last row, the last row being a 1, unless you go to the trivial zeros, the multiplication problem would be a question of repeatedly doubling the right-hand number and halving the left-hand number so that the final row would have the correct product because of the identity X. And this is an identity. I couldn't find the triple barred equals mark. x times y is identically equal to 1/2 x times y. Okay? So, for instance, if you take something simple like 8 times 9, okay, and take half of 8, 4 times 18, right? 2 times 36, and 1 times 72, and you scratch out these numbers because you have even numbers over here, then notice your answer is 72. 8 times 9 is 72. And notice what you've basically done is you've used this equation over and over again. You said, well, if I took half of 8 and double this number, 8 times 9 equals 4 times 18 equals 2 times 36 equals 1 times 72. And then if you allow yourself the freedom of saying 1 times any number is identical to that number, that is to say you knew this additional rule of multiplication that Svetlana apparently uses in her. Well, some of us use that, okay? All right, so to get a picture of that, look what happens when we multiply 28 by 709. Again, okay? The first three rows tell us that 28 times 709 equals 14 times 1418. And finally, that equals 7 times 2836 because of this basic formula over there, right? Okay? Now, but at this point, notice that you take 7 and split it in half, you'd actually have 3.5 if you kept the 0.5, right? So this equation would actually say 3.5 times 5772, and it would be accurate in reflecting 28 times 709. But instead, we said 3 times that. That means we have a remainder situation going on. In other words, if you look down at this equation down here, I got a extraneous little. See, look at the equation down here. We're talking about 7 times 2836 equals 3.5 times 5672 equals 3 times 5672 plus half of that, which is this number here. So that's why we put that in our keepers column to add back later. See what I'm saying? So now you see basically how it works, okay? And that, so whenever you have an odd number over here, you have a situation when you have it where you're leaving the number behind as a keeper because think about it, you'll see it's true. So we keep the extra 2836, we keep the 5672, and of course down at the bottom, we always keep that bottom number 1 times that. See what I'm saying? All right, because 1's always an odd number, and this process always terminates at 1 unless you keep going with a bunch of zeros, which is an infinite stack of zeros. Like you go the turtles all the way down. Refer that. Okay, for a simple example, take a look at 8 times 9 and 9 times 8. Notice that 8 times 9, some folks are surprised, equals 9 times 8. But notice your keepers are different over here. 8 times 9, this halving sequence terminates in 1 with double numbers all the way above, and this halving sequence has an odd number here. So you have an 8 left behind there, and down here 1 and 64. Notice that 64 and 8, however, adds up to 72. So this establishes to our satisfaction the basic identity of A times B equals B times A with real numbers, complex numbers, but not for every possible mathematical type situation. Okay,
so what does that say about the binary numbers? They're different, even though they're the same?
The binary numbers are different, even though they're the same?
Well,
now see, now if you're thinking about converting to binary numbers, that only works when
that only works when the right-hand number is a 1. You see, Tim?
Yeah.
The conversion to binary numbers works because you started with a 1 here. So you have to be kind of like Ivan and be silly enough to do it this way.
Okay.
You know, multiplication by 1. But anyway, let's
Gotcha.
go on. Anyway, 8 times 9 equals 9 times 8. We're happy with that, right? So when you add up your keepers, you get, in each case, the correct process. So this works because 2 is special, right? 2 is a special number. Almost as lonesome as 1 in the old Tom Jones song. But even numbers and odd numbers is a nice split. But what's so special about 2? On the planet Skidgdeech, 3 is considered specials. Numbers divisible by 3 are called Kiji numbers, and Kiji means special in Skidgdeek. So how would Skidgdeek peasants multiply? Well, here's an example. Take 28 times 709. Divide the first column by 3, and as per your halving column, and triple the second column. Okay? And notice that if you work that on through, you'll 28, divide by 3, throw away the remainder, divide by 3, no remainder, and so forth and so on. Notice you'd be crossing out these 2 rows because the left-hand numbers are even in terms of 3. They're like even numbers. They're divisible by 3, perfectly divisible. So you cross those out, add those up, 19,852, and Miss Hebda can check that on her calculator. Bear in mind, this is about midnight when I did this last night. This is my second PowerPoint, so you're so proud. Now, Svetlana, hanging out over by the dig, she heard about Skidgdeek peasant multiplication from an archaeologist who dug up some remains of a Skidgdeek spaceship that crashed over Siberia in 1906. Y'all probably heard about that. Okay? Some people are well educated. You heard about that? Okay. It blew down a bunch of trees and left a few remnants behind in the Soviet Union, and it's kept all this secret over these years. But Svetlana was in the village next. She's a curious soul. So she went over and talked to some of the archaeologists. We're always glad to talk to her. Ivan wanted to go out with Svetlana for a long time. She says she'll go out with him if he can master Skidgdeek peasant multiplication. She shows him these 2 charts, which we just talked about. Okay? Ivan takes the charts home and studies on them. An old hand at RPM, he eventually sees the pattern. Instead of even and odd numbers, halving and doubling, now the game is to take thirds and triple and throw away the rows whose first column numbers are multiples of 3. Y'all agree with that? Looks good so far? Okay. I've got it, Ivan tells Svetlana the next day. Very well, she answers. Then show me how to multiply 29 times 709. Okay, so he gets down a piece of paper. Look at his halvers column. I mean, his thirders column over here, you know. He takes a third of 29, gets 9, throws away the remainder. Ever so? Scratches through, gets the same number, 19,852. That's funny, says Svetlana. 29 times 709 is the same as 28 times 709.
Does he have 709 less?
Yes, so, says Ivan proudly. You want to go ice skating out on the lake tonight? Ivan's ready to go. He won that one, right? For a simpler problem, try Ivan's method to multiply 9 by 11 by Skidgdeek peasant multiplication, and then to multiply 11 by 9 by Skidgdeek peasant multiplication. To Ivan's amusement, to Svetlana's amusement, Ivan gets 9 times 11 equals 99, and 11 times 9 equals 90. Once again, disproving this well-known identity. You know, y'all want to see how that happens? Just out of curiosity. Because we've been assuming this commutativity of multiplication all our lives, and now it's being called into question by none other than a Russian peasant. Bless his heart. But he's really got other things on his mind. So what is he going to do? 9 times 11? Excuse me. 9 times 11, take a third of 9. What do you get? 3. And triple that. Take a third of that. 99. Go through and mark out everything that is not divisible by 3 in the first column. Add up, you got 99. Looks good, right? 9 times 11 is 99. Okay, what about 11 times 9? Well, what's a third of 11? It's 3, right? And then, yeah, well, we'll show later, man, or something. At least we do in Russian peasant multiplication. 27, 1, 81, right? And let's see, so we cross out everything that's divisible by 3 in the left-hand column, and we got 90. Everybody agree? All right. Well, there's a subtle difference between Skidjig peasant multiplication and Russian peasant multiplication. And here's where we'll get into that. To make a long story short, let's look at the remainder column as we did with Russian peasant multiplication. Look at the remainder when you divide, say, 29 by 3. The remainder is 2, not 1. See, the remainder here is 1. If you took this remainder 1 and multiplied it by 709, you'd have your keeper's column here, which is what Ivan has inadvertently done. On the other hand, if you take your remainder column here and multiply 2 times 709 and put that in your keeper's column, you'll notice that you will get the right answer down here. So you have to take into account how many pieces of the puzzle you've left behind at each step. Okay? So, in these charts, we've multiplied the remainder column times the triples column before adding. And you can think about why that's necessary at your leisure. I asked the rhetorical question, why is that necessary? But it's too complicated to answer for this moment. But just to show a little bit further, we are ready to write the number 1906 as a ternary base 3 number. If you know anything about the base 3, you'll know that it has 3 digits involved, 1, 2, and 0. And so this is part of a spreadsheet prepared by Professor Hashim with the use of quotient and the mod. The mod function picks up a remainder upon division. It's like modular arithmetic, which is also a little bit different from this regular arithmetic you're talking about here, CJ. So you do that gives us our remainders, and then in this last column, I've tricked it out to multiply the number in the remainder column by the number in this column. So you got 1 times 1, 2 times 3, so forth and so on. So all that adds up there. But notice that the number 1906 in the date of the spaceship wreck, I think that's right. Y'all might have to look that up. Look up spaceship wreck in Siberia.
It's good.
It's what?
Spaceship wreck?
Yeah, spaceship wreck in Siberia. Yeah.
I think they weren't not capable of space flight back in 1906.
Well, this was not one of ours and not one of the Russians. This was an off-Terra spaceship, you know.
June 30th, 1908.
Say what?
June 30th, 1908.
1908. I'm sorry, I got the year off a couple of years. I'm sorry.
By 2, a remainder of 2.
Right. Okay, but anyway, notice that this number 2121121 represents 2 times 3 to the, what is that, 6th, 3 to the 6th, 3 to the 5th, 3 to the 4th, 3 to the 3rd, 3 squared, 3 to the 1, 3 to the 0. So that's what's called a ternary number, a number written in base 3. If you study, actually, we can talk Goder into doing it sometime. He gave an excellent presentation for the Math Club one time on Cantor's work with set theory, and the original fractal number, the original fractal figure that Cantor developed was based on ternary numbers, base 3 numbers expressed in base 3. So there's some interesting work with the base 3. And the base 2 numbers are the numbers, of course, that are used by modern computers because they like to, they keep things real simple. On, off, on, off, on, off. On is 1, off is 0, and so forth and so on. So it's real simple for a computer to keep track of. As for us American country boys and Russian peasants and various other folks, one of my students came by and helped me format my second ever PowerPoint. That's why we got this nice little background on it. And special thanks to my colleague, Dr. Hashim Saber, for valuable assistance with programming Excel to do Skidjic peasant multiplication from across the universe. Y'all have any questions?
Yeah.
I knew you would. CJ, let me get a drink of water.
Yeah, that gap I was talking about last time, I can understand how that happened in the base 3, but how the gap happened in base 2?
Base 2?
Yeah.
Well, experiment with it a little bit. If you like, I'll send you some other. If you like, this is available, and in fact, I'm going to post this on my shared class files under special folder, and you can have the Excel spreadsheet to play around with. If you're interested in dealing with Excel, getting it to work your math problems for you. And there's some work on there by me, myself, and Hashim. And there's also this PowerPoint, which I think explains, and then, if not, just formulate get your answer down, get your question down on a piece of paper for me.